What if I told you that one of the biggest leaps forward in technology wasn't some new supermaterial or a crazy powerful AI, but just a number that's been hiding in plain sight all around us in nature? Okay, let's get into this because what we're looking at today is a discovery in fluid dynamics that is just, well, it's as elegant as it is revolutionary.
And let's just start with the headline, the number that completely changes the game. 64%. A 64% reduction in hydrodynamic drag. That's not just a small improvement. That is a fundamental shift in how we can move fluids through tiny little spaces, all from one single simple change.
So that's the big question, isn't it? How on earth can something as basic as the angle of a split in a pipe have such a massive effect? An effect that, according to the research, seems to completely defy the classic predictions we've relied on for fluid resistance. This is the mystery we're gonna unpack. All right, so to really get the solution, we first have to understand the problem. We're diving into the world of microfluidics. We're talking about incredibly tiny channels used for things like medical diagnostics or cooling computer chips. And at this tiny scale, just moving liquid around efficiently is a huge, huge challenge. This right here is the heart of the problem. For decades, if engineers needed to split a tiny fluid channel, they'd just use a simple 45 or 90-degree angle. I mean, it's easy to design, right? But it's horribly inefficient. It creates all this turbulence and wastes so much energy. The real challenge has always been to get that perfectly smooth, efficient flow you see on the other side.
And there's a scientific name for all that chaos, enstrophy. It's basically a measure of the little whirlpools and eddies that form when a fluid is forced to make a sharp turn. The best analogy? It's a microscopic traffic jam. The water molecules basically slam into each other, they lose energy, and the whole system just grinds to a halt. The goal is to get rid of that enstrophy, to clear the jam.
So if our standard engineering angles are the problem, where does the solution come from? Well, it turns out the answer wasn't found in a high-tech lab or a computer simulation. It was hidden in the universal patterns of nature itself. And this is the part that is just so cool. The breakthrough didn't come from a stronger pump to force the fluid through, or some new slippery coating for the pipes. Nope. The solution is purely geometric. It's a single, specific number. And that number comes from the golden ratio phi. Yeah, that golden ratio. It's a constant that just shows up everywhere in nature, defining these perfect patterns of growth and efficiency. You see it in the spiral of a galaxy, the way trees branch out, the chambers of a seashell. So the researchers thought, what if the ideal path for fluid follows the same universal rule? So how do we get there? The math is actually pretty direct. You take the golden ratio, which is about 1.618. Then you calculate its geometric projection using the arc cosine function, just like you see here. And what you get is this one incredibly specific angle, 38.2 degrees. Not 38, not 39, precisely 38.2. And this brings us right to the core of the whole discovery. How does this one specific, nature-derived angle manage to tame all that chaos and completely eliminate that microscopic traffic jam we called entropy? The answer is just beautiful. The source material explains that this angle isn't just some random sweet spot. It actually mathematically mirrors the fluid's natural, undisturbed path of expansion. It's like the perfect gradual lane change on a highway. It allows the fluid to preserve its natural flow, its natural momentum, and it prevents those chaotic vortices from ever even forming. It's not fighting the physics of the fluid, it's working with it. And this just says it all. Look at that. On the left, that's the high drag you get with a standard split. And on the right, that's the result of the 38.2-degree golden angle. I mean, it's not even a subtle difference, is it? It is a game-changing drop in resistance. This is the kill shot data from the experiment, just undeniable proof. And here on this table, we're just seeing the numbers behind that incredible chart. With your standard designs, you get high entropy, that chaotic vortex generation. With the 38.2-degree design, you get that amazing 64% drag reduction. And the why is the key. The standard design creates turbulence, while the golden angle design geometrically preserves the fluid's natural flow. So a 64% reduction is impressive, for sure. But what does it actually mean for the real world? Why does this single discovery matter so much? Okay, this is where it gets really, really exciting. This isn't just some interesting academic finding. This breakthrough could completely revolutionize so many fields. Think about hyper-efficient lab-on-a-chip devices for way faster medical tests.
Or advanced cardiovascular implants, like stents that work more harmoniously with your blood flow. We could see a whole new way of cooling our computers. And the best part? All of this could be done with tiny, ultra-low power pumps, which would save a massive amount of energy.
And that leaves us with this final, fascinating question. We just saw how a secret from nature, expressed as a simple angle, solved a huge problem in fluid dynamics. It just makes you wonder what other great engineering challenges out there aren't waiting for a new material or more power, but are just waiting for us to discover the right geometry.